Well, hello and welcome back to Statics Engineering 211, and I wanted to work on a new subject today, that of friction. So let's talk about that. And when we talk about friction, we're going to talk about a dry friction, or sometimes they call it coulombic friction. So I'll say dry friction. The mechanicals will go on and talk a lot about fluids, friction of fluids and whatnot, lubrication, where you have a bearing, maybe a bearing surface with a thin film of oil between another bearing surface and whatnot. We're not going to get into that. We're talking about dry friction, and that's really just a force that opposes motion in one direction. Probably the best way to describe it is with a Freebody diagram. So let's say that we have a weight or something. So we've got some weight W, and it's going to have some normal force supporting it. So we'll say that's N, and maybe we're trying to pull it this way. We'll say we've got some tension force T pulling on it. And we could have some friction force here. We'll call this F sub S. And that is our friction force, we're going to say, is equal to then mu sub S times the normal force N, where this is our coefficient of static friction. Okay, our coefficient of static friction. And we could actually look at resolving these forces if we wanted to. We could talk about the resultant, of course, being like that. And we'd get some angle of friction in here. We could talk about this as phi sub S. Clean up the drawing just a little bit there. So this would be phi sub S, where that would be our angle of friction. Our angle of friction. And if we look at that, we could say that that's really equal to what the arctangent of the opposite side, which is F sub S, which is going to be mu sub S times N divided by N. So when we cancel the N's, we'd say that this is really equal to the arctangent of mu sub S. So a lot of times when you look at certain materials, maybe wood on concrete or steel on steel or concrete on earth or something like that, you can look up and they will report to you what the coefficient of static friction is, mu sub S. Or they might give you the angle of friction. In any case, they're essentially giving you the same thing when you see the relationship between these two. Now typically, the coefficient of friction, mu sub S, is going to be greater than 0, and usually, most of the time, less than 1. Okay? If you start getting over 1, there are some cases, maybe in a very sticky tire on a dragster or something like that, but for most of the things, when we're looking at a rope going over a piece of wood, or maybe a rubber belt sliding on a piece of steel, or maybe for the civil engineers, we look at building a retaining wall or a dam, and we've got some concrete on earth. Most of those coefficient of frictions are going to fall in between 0 and 1. And this coefficient of friction, it's unitless. It has no units. Really, it's just a ratio then of this normal force. So we multiply the normal force by this coefficient of friction, and we get the friction force. Okay. Now we can actually look at maybe a side note here. This is static. Okay, what happens if you have a situation where this is moving along? So we could talk about this thing where it's got some velocity and it's moving along. I've got my tension force here. I've got W, and we've got the normal force and the friction force, and we can say that this is F sub K, which is equal to mu sub K times n. And if you wanted to, you could do the same thing, resolve it, and talk about the phi, the angle phi, phi sub k, and whatnot. I won't get into it too much, but this is going to be our kinetic coefficient of friction. U sub k is defined as our kinetic coefficient of friction. Okay, our kinetic coefficient of friction. So one thing I'll tell you is that the static coefficient of friction is almost always greater than the kinetic coefficient of friction. If you've ever maybe tried to get a heavy box that's sitting on a warehouse floor or something moving, it's a lot easier to keep it moving than it is to get it moving. There's always a great example of this in modern movies. If you've ever watched the one of the epic films in terms of cinematography and whatnot, the Ten Commandments, and they have the scene in there where the Israelites are subject to the Egyptian oppression and whatnot, and they're being used as slaves, and they're trying to move great big stones. And they have all these slaves pulling on the stone, and they have this lady, this grease girl, that's greasing, literally putting grease on the skids. And of course, her you can almost see it coming as you watch the movie. I don't want to spoil the movie too much for you, but you can get the movie and watch it, and you'll see her dress get caught under the stone. And of course, her hero, I believe that's Moses, comes down and stops the stone. The taskmaster, the Egyptian taskmaster, is just furious about this, and comes up and says, "Why have we stopped the moving stone? We do." And Moses says, well, the girl, he stopped it because he didn't want the girl to get run over by the stone. And the taskmaster says how they never stop a moving stone. And of course, that certainly seems inhumane, but he had a good handle that the static coefficient of friction was greater than the kinetic coefficient of friction. So you can take that for what it's worth. That's one way of remembering that, although probably not a good way to apply it. So these are very general terms. This is going to work in most cases. This works in almost all cases. We can probably find some odd material under some odd situation those things won't be true. But in most of the cases, most of the things you're going to deal with in civil engineering and mechanical engineering, that is very true. Well, let's try and put this together into a problem. And the only thing I would say before we head on to that problem is that free-body diagrams are very important when we get to this point. Maybe I'll emphasize that, free-body diagram here. Because you look at this, if this is moving in this direction, we have to have the friction force here. If all of a sudden we were to have this move in the other direction, we'd have to apply the friction force in the opposite direction. So the direction of the friction force is critical, and the free body diagram is going to help us sort that out. So let's tackle an example then. So in this example, pretty simple scenario. We've got a pulley up here, and we've got some sort of a weight. Let's say that this is 100 kilograms. This comes up over here, and we've got this weight hanging. We'll say that this is m sub naught, and we're going to say that this is 20 degrees. And we've got the coefficient of static friction between the block here and the ramp, which is given as 0.3. Okay? So we'd like to find the range of m naught. We'd like to find the range of m naught for no motion up or down the ramp. You could imagine that if m naught were increased to a large value, it would eventually start to pull this mass up the ramp. And you could imagine conversely, if you were to reduce the weight here, it would eventually allow the mass to slide down that ramp. So let's give that a try. Let me fix that angle there. That's a little bit shabby. See if we can get that a little better. There we go. Okay, so we got 20 degrees there. Well, the first thing, and oftentimes friction problems require this of us, is to work multiple cases. In this case, we're going to have to look at motion up the ramp or motion down the ramp. So let's first look at motion up the ramp. So if I look at motion up the ramp and look at that free body diagram, I've got something like this. I'm going to have the tension force, T, acting up. That's what we have there. That's that tension force, T. And then if I take 100 kilograms, I'm going to have 100 times 9.81, I'll just say 981 newtons, 9.81, the acceleration of gravity, times that 100 kilograms. Remember, and this is a good point with this, that our free body diagram is always a diagram of forces, never a diagram of masses. So I'm going to convert this to a force. And if I've got motion up the ramp, the friction force is impeding that, trying to push it down the ramp. So we'll say F sub S, which is equal to mu sub s times the normal force. And where's that normal force? Normal force would be perpendicular to the ramp, so we have something like that. Okay. Now, I think I'll go ahead and look at this. I could talk about this being the x direction, so I'm going to rotate my coordinate system, and this being the y direction. And having said that, I would be then looking at, what, 20 degrees in here, wouldn't I? 20 degrees. For some reason, I can't write that 20 degrees very well. So I've got that 20 degrees in there. Okay, 20 degrees in there. I'll try and clean that up before I make the PDF, but we've got 20 degrees there. So have we got everything? We've got the weight of this acting to the center of the earth. We've got the normal force of the ramp pushing back on the block. We've got this tension in this rope or cable. And we've got the friction force. If we're looking at motion up the ramp, our friction force is resisting that. It's going down the ramp. So what I can do here is if I sum the forces in the y direction, so sum of the forces in the y direction, I guess I'll just work it right here. Sum of the forces in the y direction is equal to 0. What do I come up with? I've got the normal force minus 981 times the cosine of 20 degrees. Anything else? I think that's it. So that's equal to 0. So I can say that the normal force is equal to 981 times the cosine of 20. Which gives me what? 921.8. Let's just call that 922 newtons. Well, that will probably be handy when I sum the forces in the x direction. So let's do that. Summing the forces in the x direction, setting that equal to 0. What do I have? I've got the tension force T minus this friction force. And I could write F sub s, but I don't know anything about F sub s. I think I'll use mu sub n. Mu sub s times n, mu sub s times n. So I've got T minus that, and then I've got this component of this one, so minus 981 times this time the sine of 20, right? Okay, so I could say then that T, if I'm trying to find the tension T, that's going to be equal to mu sub s times the normal force plus 981 times the sine of 20, which would be mu sub s 0.3 times the normal force 922. That's why we had to find this one. And I mean, had we done this equation first, we would have then just had to have the patience to go back and do this one. And we add to this 981 times the sine of 20. Let's see what that equals. What do we come up with? 612 newtons. Okay, so that's 612 newtons. We're assuming that there's negligible mass in this cable or rope. This becomes a much more difficult problem. We have to take that into account. Although we're studying friction, we're going to assume negligible friction in the pulley there. So we can really just say that this mass m naught, if we look at the weight of this thing, the weight would be equal to m naught times the acceleration of gravity g. So solving this, then I get that m naught is equal to the weight divided by g. So I'll take this 612 newtons and divide by 9.81 meters per second squared and come up with 62.4. So we'll say 62.4 kilograms. That would be the amount of mass that for m naught to have motion up the ramp. Okay, so that's the high end on this. Let's look at the other one, which would be the low end motion down the ramp. So let's go to that one. So down the ramp, and that free body diagram is going to look like this, where I again have the 100 kilograms, and that's still going to be 981 newtons, because we always have free body diagram of forces, not masses. And then we've got some tension force T going up the ramp, but since this is trying to go down the ramp, the friction force is going to be like this, trying to push it back up the ramp, isn't it? So I'll have this F sub S is equal to mu sub S times N, not mu sub N times N, mu sub S times N, mu sub S. U sub S times N. And then, of course, this is N, perpendicular to the ramp. Again, if I look at a XY coordinate system, I'm going to take this as X. I'm going to take this then as Y, and I can say that that is 20 degrees. So with that, if I were to, have I got all the forces? If I go back and I look at the picture here, I've got the weight, I've got the ramp pushing against the body, I've got the tension in the cable here, and then since we're looking at motion down the ramp, I've got the friction force opposing that. So I think I'm good. So if I sum the forces in the y direction here, setting that equal to 0, again I have the normal force, then minus 981 times the cosine of 20, and of course we get the same normal forces we did before. Let's say 922 newtons. This should be different though. Some of the forces in the x direction, setting that equal to 0. And I think I'll go ahead and take a positive up the ramp. So I'm going to have T, and then I'm going to have positive, so I'm adding the friction force this time, mu sub S times N. But I still have to subtract the piece over here, that piece there, which is subtract 981 times the sine of 981 times the sine of 20, right? So I could solve for T. T is then equal to 981 times the sine of 20 minus mu sub S times N, which would be 981 times the sine of 20 minus mu sub S. We said that that was 0.3. 0.3 times the N that we found, which is 922. So that turns out to be equal to, and we run through those numbers, and we come up with 58.9 9? Yeah, something like that. Pretty close to 59. Why don't we just call it 59? 59 newtons. And again, we know that m naught would be equal to W divided by G. So I'm going to take that 59 and divide by 9.81. This newtons and meters per second squared. And that turns out to be equal to 6, pretty close to 6 kilograms, 6 kilograms. So it looks like our range for no motion up or down the ramp is going to be that m naught is greater than or equal to 6 kilograms and less than or equal to 62.4 kilograms. So that would be our answer. If the mass on this guy, if the mass here gets less than 6, it's going to slide down the ramp. If this gets greater than 62.4, you're going to have motion up the ramp. So it's a good problem, and a typical friction problem. Oftentimes with friction problems, you end up having to solve a couple of different cases, a couple of different scenarios, which brings me to my next scenario of tipping and slipping. Get through some pages here. So let's talk a little bit about tipping versus slipping. If you've ever done this, maybe you're trying to move the refrigerator or something, so you reach out and you grab the refrigerator, and it doesn't slide out like you expect it to. All of a sudden, it starts to, tip over on you. So we need to talk about that, slipping and tipping. Slipping and tipping. Okay, well, let me look at slipping. So if I have slipping, and we'll take something maybe like that refrigerator. Let's say that we have something like this, and I apply a force here to the top of it, and we're going to say that it has some weight acting down through its centroid like this. And that we'll say that this is the base dimension over 2. I need a better pen for this. Clean this up a little bit. Okay, so we're going to say that this is the base dimension divided by 2, and this is the base dimension divided by 2. And we'll say that this is the height, h. Okay. So this would then be the weight, W, acting down. And what do we have here? Well, if we have slipping, we're going to have the friction force here. We'll say that that's F. And we're going to have the normal force somewhere in here. And I'm not really sure where that normal force is. We can say that this distance is x. This is the normal force. And when I have slipping, I know that x, I don't know that much about x. I know it's going to be somewhere between 0 and b over 2. It's going to be somewhere in this region here. Okay, it'll be somewhere in there. The good news is I do know that the force F, that becomes the friction force. It's going to be equal to mu sub s times n. Okay, classic slipping. I don't necessarily know where the normal force is going to be applied, but I do know that the friction force is mu sub s times n. Or now if I look at tipping, let's see what we get for tipping. So again, I'll take a very similar or exactly the same thing. Same refrigerator or vending machine or whatever you're moving. And we're going to apply this force up here. And we've got the weight W acting through the mass center. This is again B over 2 and B over 2. And here if I have tipping, you can imagine if you push it here, it's going to start to tip at this corner. So what you're going to have is you're going to have a force there, and you're going to have the normal force. And I'll call this force F. We're going to talk about that in a moment, and then the normal force. And we can talk about this distance in here. We'll say that that distance is x. So if I have then tipping, I know that x is equal to b over 2, that this normal force has got out to there. So that's the good news. I know a lot about where that normal force is. The bad news is that the force here is not the friction force, because if it's tipping, it's not slipping. So this friction force is not developed yet, so this is going to be less than, it might be equal to, just the verge, but less than, I'll emphasize less than mu sub s times n. Okay? It'd be less than mu sub s times n. So in a slipping situation, I don't necessarily know where the normal force is, but I know the force F is the friction force. And in tipping, I don't necessarily know what this force is. It's not the friction force. Okay, it's less than the friction force, but the good news is I know where n is. Well, your author has a couple of good examples. I'm not going to necessarily say the example number or the page number because everyone has different versions of the textbook, but if you go into the chapter on friction, usually what they look at is there's an example where they've got this incline, maybe it's a dump truck or something, and they're tipping this up, and they have this refrigerator or vending machine or something in there, and you're asked to figure out what's going to happen. Is it going to slip first, or is it going to tip first? So you have to oftentimes look at slipping, and you have to look at tipping, and then see which one's going to be more plausible. I think I'm going to tackle, because your author does a pretty good job of that one, and I encourage you to read through that. I'm going to tackle a slightly different problem, and probably a harder problem, or a harder problem to get your mind around, although when you step away from this, when we're done, I think you'll look at it as a very similar problem to tipping or slipping. And what this problem is I have some sort of an industrial truck or a Jeep or something, and I'm trying to push this paper roll, or you can take it as anything you want, a log or a roll of paper or something, up an incline. And it's a 30-degree incline. And we're told that it's 12,000 newtons, so about 2,500 pounds, a little less than 2,500 pounds. And our numbers are made easy. We're told that the coefficient of static friction and kinetic friction between the roll and the ramp, that would be right here, is equal to 0.4. And then we're told that the coefficient of static friction and kinetic friction between the roll and the truck, that would be right there, those are all 0.4. So I have to look at two cases on this. The first case is slipping at the truck. Okay, so slipping at the truck. So what this is going to look like is if I take this roll, I'm going to, if it's slipping at the truck, it's essentially, if you imagine it slipping across this truck, it's pivoting at this point here, isn't it? Okay, so the flip side of this is tipping at the ramp, isn't it? Tip at ramp. So let me put those in here. I'm going to have this force here. I'd probably have some normal force perpendicular to that ramp. Okay, we'll say that that's the normal force. And then I'd have some force here. I'll call that F2. Over here, I'm going to have the truck pushing on this thing. I'll say that that's P. And I'll have the force F1 right here. Okay, and what we're looking for in this thing is the force that the truck has to push on with this. So maybe we'll say P. You could ask that in a variety of different ways, the tractive force that's developed between the tires and the ground. But basically, we'd like to figure out that the force that the truck needs to push this up the ramp. Okay. Let me put some geometry on here. I'm going to assume that this has some radius, capital R. We weren't told that radius. Hopefully, it will cancel out. We'll look at this. I guess I better put the weight in here. That's that 12,000 newtons. And then I have, let's see, if that's 30 degrees, this is going to be 30 degrees, isn't it? Okay. So if I have slipping at the truck, F1 is a friction force, isn't it? But F2 is not equal to mu times n. So that leaves me with a big question mark on F2. Okay, so I don't know F2, I don't know n. So where's a good point to sum the moment about? Probably be here. We'll call that C, the contact point. Okay, call that C, the contact point. So I'm going to do that. I'm going to sum the moment about that contact patch or contact point. I'm going to set that equal to 0. Maybe I'll go ahead and take counterclockwise as positive. So I'm going to say that I have this force P, and that's going to be acting through a distance of what? R cosine 30? Is that right? Yeah, I mean, I'm just looking at a triangle there. I have a triangle, this distance here. This would be R. This is 30. So this distance is, of course, R cosine. This is sine, isn't it? Okay, so R cosine 30. Then I've got minus F1 times what distance do I have there? That's this distance here plus this distance here. Isn't this distance R? Yeah, so I'm going to have R plus R sine 30. Okay, and then what else do I have? This F2 intersects that point. That's good because I don't know F2. I don't want to deal with that. And I don't know it. So that intersects that point. So this is a great point to sum the moment about. But I do have this 12,000. So I should subtract off 12,000 times what? R sine 30? Okay. Well, it looks like I have quite a few unknowns. I've got P that's an unknown. I've got F1. But remember, F1, if I have slipping, we said slipping at the truck, right? So F1 is really a friction force. That's going to be equal to mu times P. So let me substitute that in there, mu times P. So now we don't have F1. We know mu. P is still an unknown. R is an unknown, but I think everything has an R, doesn't it? If I divide everything by R, there's an R here, there's an R there and there that could be factored out, there's an R there, so I can divide by R, and essentially come up with 0 is equal to P times cosine 30 minus mu times P, so that's 0.4 times P times 1 plus sine 30. And then what am I going to have? Minus 1200, not 1200, 12,000 times the sine of 30. Well, with that, we could definitely solve for P. It's the only unknown. When you do that, P turns out to be equal to about 22.6 kilonewtons. Okay, about 23,000 newtons. Well, I'm going to, I know that this is equal to F1, so I'm going to, with that, say that F1 is equal to mu times P. So we'll put that in there, and then F1 turns out to be about 9 kilonewtons. Okay, about 9 kilonewtons. And I'm just going to hold on to those, because you can imagine, and some of you may have been yelling at the TV or the computer already, but what about if it's the other way? What if we have slipping at the floor and essentially tipping at the truck here? So let's go do that. So here I'm going to say that I have slipping at the floor. So I have slipping right here, which means I'm going to have essentially tipping at the truck. Okay, so you can imagine it's pivoting at this point here and kind of back rolling around there as it goes up the ramp. Okay, so let's see what that Freebody diagram looks like. I got particularly lucky on the last circle. I don't know, I think it was beginner's luck. That's not as good a circle there. Anyway, so what do we have here? We still have the truck pushing on this thing, so we'll say that we have some P force here. And we have this force F1, which now, because we have tipping at the truck, this is not equal to mu times P. Before, remember, when we looked at this one down here, this one was not equal to mu times n. Now it's going to be equal to mu times n, and this one will not be equal to mu times P. So it's not equal to mu times P. I have the weight here, 12,000 newtons. And over here I have the normal force. And then the friction force F2, where F2 is going to be equal to mu times n. Put a little more geometry in here. We'll say that this is 30 degrees. And then this is 30 degrees. And of course, this is equal to 30 degrees. Again, I'm going to assume that the radius of this thing is r, and hopefully it will cancel out as before. Now, where should I sum the moments about on this thing? Well, I think I'll sum it here at this point t. I'm going to say that that's the point at the truck, because I don't know this. I mean, this is a problem for me. I don't know that. So if I sum the moment about this point, I unfortunately won't get p, but I won't have to deal with this one. So let's try that. So sum of the moments about t, and again, maybe I guess I'm, yeah, the same way. Same way as the last time, aren't I? Where is that? Right there. Yeah, we're doing clockwise as positive. So this is equal to 0. And what do we have? We're going to have 12,000 times, I'm summing it about this point here, right? At the truck, so yeah, that would be 12,000 times r, this force acting through that distance, then minus, this one's going to be a little more work because I've got to break these things up. I'm going to have n times the cosine of 30. That's that vertical piece there, and that's going to be acting through the distance from here to over to there, so that's going to be r plus r sine 30. And then I have to add to that n times the sine of 30, n times the sine of 30, that's the horizontal piece, and that's going to be acting through this, just this distance in here, isn't it? Okay, so that's going to be r cosine 30. R cosine 30. And then I've got to break the F2 up. So plus F2 cosine 30, that's the horizontal part there, and that's going to be again R cosine 30. And then I have to also add, isn't that, yeah, that's positive, and the vertical is positive, so positive F2 times the sine of 30, F2 sine 30, and that's acting through that total distance there, again, R plus R sine 30. Okay, well, it looks like a fairly ugly equation. Let me double check that, make sure that we're right before I try and make it better. Yeah, I think we're good. So let's see, a lot of unknowns in here. N is an unknown. R is an unknown. Does everything have an R? There's an R. There's an R that could be factored out, so that term has an R. There's an R. There's an R. This R could be factored out, so all the terms have an R. So we're going to divide by R. Okay, we'll divide by R. And then what are we going to have for F2? We know F2 is equal to mu times N, right? So we're going to make the substitution here, mu times N. We're going to make the substitution here, mu times N. So let's see what that looks like. We'll be able to say that 0 is equal to 12,000 minus N times the cosine of 30 times 1 plus sine 30. All right, yep. Plus N times the sine of 30 times the cosine of 30 plus mu times N times the cosine of 30 times the cosine of 30 plus mu times N times the sine of 30 times 1 plus the sine of 30. Let me double check that. Cosine 30, 1 plus sine 30. Yeah, I think we're good. So what are we left with? We've got mu as 0.4. Then we're left with just N, aren't we? Okay, so we could solve for N in this case. N, and the smoke clears on that, is about 45 kilonewtons. So we could say then that F2 is equal to mu times N, which is 0.4. So 0.4 times the 45 gives me 18 kilonewtons. So now it's up to us to figure out which scenario. Is it this scenario or is it this scenario? Well, we could come back here if we wanted to, and we could sum the forces in the horizontal direction, setting those equal to 0, and with that we would get P. Okay, and you could do that. What would you have? Everything's vertical except for the horizontal portion of this and the horizontal portion of that. I mean, this would essentially be this friction force F2. What was F2? So you had 18 times the cosine of 30 plus, what's the horizontal piece on that? 45 times the sine of 30. And that turns out to be about 38. Okay, so you could go ahead and do that. I actually wouldn't worry about that because I could actually compare them a little differently. Will we ever get a friction force developed of 18 kilonewtons when this friction force is only required to be 9 kilonewtons? The answer is, of course, no. So we can say that this F1 is a lot less than this F2 right here. So the force required, so P is equal to 22.6 kilonewtons. That would be the answer. Okay, and you can certainly see that. Is the truck going to develop 38 kilonewtons? This is kilonewtons. When all it really needs to do is develop 22. Well, with this 22, we see that this is what governs. Okay, so we looked at, and this is very classic in these problems. You have to do the problems both ways, and then you look at the answer and you rationalize this answer. Is this P force here less than this P force? Yeah, it is. And in fact, I didn't even need to go and find this. I could. It wasn't very difficult. But I could also rationalize that the friction force, this friction force, is way less than this friction force. So I know that this case is the governing case, and it's going to start slipping at the truck way before it starts to slip at the ramp. So this is the governing case and what we'd expect to happen. Well, again, I think those are good problems. Again, this is really a slipping and tipping problem, and like a lot of friction problems, it requires you to work a problem a couple different ways and then look at the results of that. Well, let's try one last concept. If you look in the chapter where your author introduces friction, it talks about a variety of things in terms of belts and clutches and wedges and things like that. I've always been interested a little bit in wedges. And when you think about it, if you look at a bolt with the threads on a bolt, you can, let me get this arranged here. I'll get it fine and coarse. So we've got a 9/16 inch diameter bolt. Okay, 9/16 inch diameter bolt. Just not that common of a size. If you go down to a place like Fred Meyer, they might not have it. You go to a normal hardware store, they'd have it. But a lot of times they skip from 1/2 to 5/8. But 9/16 is hanging out in there. So if I look at the circumference of this, and when we talk about threads, and we could talk about the root diameter, or the mean diameter, and whatnot. But we'll just keep this real easy. Say that our diameter is 9/16 of an inch. So if I look then at the circumference, I can say that that's pi times d, right? Which would be equal to, if I use this 9/16, I'm going to have pi times 9/16, I'm going to have 1.74 inches. Let me double check that for you. Yeah. Did I do that right? I guess I get 1.77. I'll just leave it at 1.74. We'll say approximately. Okay, because it depends when you look at this what that's going to be, whether you're looking at down in the groove or up above. So we'll take it at about that. So if I look at the fine thread, and with the fine thread, this 1.5 inches, I have essentially a ramp or a wedge, if you will. And we look at this thing, this is 1.5 inches from there to there. So I have 1.5 inches. And we have, what, 24 turns? Okay, 24 turns. So if you count the turns, there's 24 turns or 24 threads. So I'll take this as 24. I'm just being approximate here. 1.74. I should probably say 1.75 or 1.77. So that turns out to be 41.76. Let's just call that 42 inches. So essentially around this bolt here, I have a ramp that is 42 inches long and has a rise of 1.5 inches. Well, if I look at the course, I have 17 turns. So my ramp's going to look a lot shorter, a lot steeper. So 17 turns, count those, I'd have 17. We could work this out as threads per inch too, but I just counted those in 1.5 inches. So I've got 17. So I'm going to take 17 now times that 1.74, which turns out to be equal to 30 inches. Double check that. Yeah, that's close enough. So I've got 30 inches to go the 1.5 inches. So let's say that you're using this in some sort of a jack arrangement to lift a load. Which one's going to be easier? The fine thread. Which one can you clamp tighter? Probably the fine thread. Which one's going to possibly slide down this ramp easier, causing to essentially unscrew, loosen up? And that would be the fine thread is going to probably stay clamped better without any locking device. Now, there's certainly practical things in terms of cutting the threads and materials, and if you're using a jack, you don't want the fine threads to get messed up. And the profile, if you're going to use this over and over again, maybe you'd want an Acme profile rather than the 60-degree profile that you have there, all kinds of things. But what I wanted to point out is you could really think of these things really as a wedge or an inclined plane or a ramp. Okay, it's essentially just wrapped around the axes of that bolt. So when you look at some of those things, and we're not going to get into that, the mechanicals are going to talk about machine design in a separate area, talk a lot more about clutches and friction fits and things like that. But I just wanted you to be aware of some of these common things and how we can look at them a little bit differently, and using some of the models that we have already developed. You could start talking about friction here and having this slide up the ramp or down the ramp and so forth. Well, that actually is all of the friction problems that we're going to do. We've got some homework problems. I encourage you to look at those. We've got two areas left. We've got to talk about centroids, center of area, center of mass, and things like that, and then mass moment of inertia. So we're getting close to wrapping up the term, and we will continue to get to that end when we meet next time. Take care till then, and thank you for watching.